Inside the question of abiogenesis and the origins of life, there has been a common theme across the entire time we have even known to ask the question in a way where we can perform experiments and try to understand it. Even though, when we look into the cosmos, we see the chemistry of carbon, the most basic precursor of our form of life, organic chemistry, we see it everywhere, from meteorites to nebulas in space. Carbon is common. Even though carbon is common throughout the cosmos, giant unstable stars belch great clouds of it out, as Betelgeuse and other stars do. That hasn't stopped us from adopting a kind of bias. Throughout the search for the origins of life, there has proven a reluctance to consider that the process might actually be easier than we thought it was. Rather, the bias was always the assumption that it was hard. But an early experiment performed by Miller and Urey in 1952 indicated that at least one part of the puzzle was not hard at all. The experiment was this. If you simulated the conditions of early Earth before life, as they were thought to be in the 1950s, we now know a lot more, but if you create an imperfect approximation of Earth's atmosphere and what it was like, and you inject abiotic nutrients into it and run electrical current through it, simulating lightning, out comes the synthesis of organic compounds. All they did was put in methane, ammonia, hydrogen, and water, shock the whole thing, and out came amino acids. And at the time, they only identified a few, but a re-examination of their samples in 2007 detected more. Now we know that Earth's normal atmospheric composition was not what they were using as their model, but actually might have gotten it right anyway. In the immediate aftermath of the massive numbers of impacts that were happening in those days, did at times make the atmosphere similar to what they were using. And importantly, the chemistry happened no matter what, very rapidly in that environment. But later work also showed amino acids naturally occurring in primitive comets from the outer solar system, not subject to the environment of that kind of an atmosphere. Nature creates amino acids, the building blocks of life. And it seems to have several ways to somehow do that. But we see it in meteorites in addition to the Miller-Urey experiments and also its successors. It is repeatable. But we also know that protocellular walls can form under certain conditions. This was shown by Deamer and Deamer in 2020, link in the description below, and a link to an Event Horizon episode I did with Dr. Deamer. Here they simply went to a volcanic pool that periodically dries out in Russia's Kamchatka volcanic region and introduced the components of cell walls, lipids, basically soap. And in that drying and rehydrating process, out came protocell walls, not at all unlike those used by life. In another instance shown by Benner and colleagues recently, demonstrated that RNA generation is apparently easy, linked to an interview with Dr. Benner below. Effectively, what they did was to add in the nutrients necessary for RNA into water, and then percolated it through volcanic glasses. And out came large, random strands of RNA. This simple answer of percolation through volcanic glasses effectively ended the decades-long debate about how RNA forms, which had ranged so far as to suggest that it forms on high uranium, radioactive beaches. The actual answer was simpler than what was expected, and it also led science to look into complex ideas rather than simple ones, as the process seems to have turned out to be. So simple, in fact, it can be repeated in a high school classroom. But now we have a new development on protocells that might suggest it's even easier and has more ways to happen than we thought. So as I mentioned, a protocell is not alive. It's a spherical membrane made of fatty molecules that resemble living cells to the point that they seem to be the precursors to them. Now it turns out that these protocell structures can spontaneously self-assemble on the surfaces of micrometeorites after they have deposited on Earth, or, for that matter, Mars. This is literally the dust that pervades the solar system, deep space, and so on, and is one of the causes of meteor showers. If a micrometeorite on Earth can do it, then chances are it can happen at any number of exoplanets. Dust is not rare in the universe. In fact, it's one of the most common things in the universe, by far. It's important to remember, however, that this is not happening in space. This happens only when the micrometeorite is down here on Earth. It's also not happening in solution, but it can happen on the surfaces of a micrometeorite. The new paper by Gozen and colleagues is somewhat surprising in this regard, in that it does not seem to require a solution of liquid for these protocells to form on surfaces. The reason is that certain surfaces have available energy. The exposed surface has atoms that do not have a complete set of bonds. Micrometeorites have such surfaces that can use that extra energy to perform the kinds of chemistry observed with these protocells. So what the team did was take 3 samples of 3 different kinds of micrometeorite and suspend them in petri dishes that contained lipids. In fact, the same kind of lipids that are used by simple archaeolife on Earth. 3 samples, however, is just a beginning, as there are numerous other types of micrometeorites. But the experiment does show that it can happen with these materials if you have the ingredients. Of course, nothing says that this was the mechanism life on Earth first used for cell walls. There's also the hot spring evidence. But more that there are now 2 paths to cell walls in nature, chemically speaking, if you have the lipids. And given that organic compounds are found in micrometeorites, to some degree, the micrometeorites do come with their own ingredients. If this is how cell walls first occur, however, the implication is that this is not a difficult process to form a protocell, and given that it's run-of-the-mill space dust involved, then this is occurring everywhere in the universe, to the vast majority of planets in the universe, to varying degrees. It's interesting that it's been demonstrated to happen now, because it had been an open question for some time. The physics of this mechanism was murky, and it was uncertain if it could happen or not, but it does. What else is interesting is that the protocell walls that form on the meteorites are actually markedly different than those that form in solutions, like the hot springs, as to how they are arranged. In the meteorites, they form networks with nanotube connections between them that allow them to transfer their contents, meaning that these protocells not merely just form and exist, but actually can perform rudimentary chemical signaling between themselves. From the very outset, they start doing some of the things that life and our complex cells do. And this isn't the only recent discovery that may hold clues to the environment of early Earth and its chemistry. There is a primitive plant that still exists called the smooth horsetail that grows in places like the Rio Grande River, where these samples grew. And what it does is basically filter and distill water as it moves through the root system and up the stalk of the plant. So oxygen atoms in water tend to have 8 neutrons, but there are heavier isotopes with 9 or 10. Evaporating water tends to remove the lighter isotopes first, leaving the heavier ones behind, which is used in science to understand the history of a water sample. These plants, which first appear in geologic history 400 million years ago during the Devonian, seem to do something unexpected, along with a number of other desert plants. So these horsetails are long, slender, stalk-type plants that have millions of holes in their matrix that are equally spaced for water movement. As water moves up the tube-like stalk, some of it evaporates, causing the water to become distilled. So the scientists sampled the isotope ratios of the oxygen of the water at various points up the stalk. By the time the water gets to the top of the plant, it has an isotope ratio found nowhere else on Earth. This literally looks like meteorite water. And if blindly tested, scientists would conclude that the sample most likely is from a meteorite, when in fact a plant species distilled it that way. The most obvious use of this research is in water testing. There can be very puzzling samples that show up in water analysis that the action of plants like this might be relevant to. And indeed, once the profile of this distilled plant water was compared against some anomalous water samples, it was a match, explaining some previously thought to be odd samples. But this also has implications on paleontology. The ancient horsetails could actually grow up to 30 meters tall, which means that such enormous stalks could distill the water even further, leaving even stranger isotope ratios. This could have contributed to what was available to Devonian and later ecosystems, and by studying traces in the fossil record, it may allow for more information about ancient waterways and ecosystems to be teased out. Helping this out are small grains that exist in the horsetail stem, called phytoliths, that preserve as fossils, and these have different isotope ratios on their own that change with humidity, which in turn affects evaporation rates. This means that fossils from that period allow you to measure what the ancient humidity in the period was like, why the water in these plants looks like meteoritic water, and what exactly the plant needs to distill water like this remain mysteries. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently eyeing the plant suspiciously again, or hungrily. For the gardeners, it's pepper harvesting time, and I actually got a very nice crop of bell peppers this year, along with many varieties of chili pepper and soon sweet peppers. Fun time of the year, albeit very hot. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.